In this video, I will be discussing how to integrate trigonometric functions. In the previous video, I discussed 7 formulas already. So here I will add 6 formulas to our 7 formulas that we had in the previous videos. Given u as a differentiable function of x, then the following formulas can be used. Formula number 8, that the integral of sine u du is equal to negative cosine u plus c. Formula number 9, integral of cosine u du is equal to sine u plus c. And this is sensible, the formulas, because we know that integration and differentiation are inverse operations. Because the derivative of sine u is just cosine u there. And the derivative of negative cosine u is also sine u. Also here in the formula number 10, it states that the integral of secant squared u du, it is equal to tangent u plus c. Because the derivative of tangent u plus c is secant squared u. Also in the number 11 formula, that the integral of cosecant squared u du, this is equal to negative cotangent u plus c. And so with the last 2 formulas, you can see that the derivative of secant u plus c is just secant u tangent u. And also the negative cosecant of u, the derivative of this is this. So let's apply these 6 formulas in our examples. So example number 1. What is the integral of secant squared x times tangent squared x dx? Now looking at this example, we haphazardly think that we can readily apply the formulas above. But actually, we cannot apply because here in our integrand is just a product of 2 functions, the secant and the tangent. And remember, there is no straightforward formula in integral calculus for product. So what will you do is to apply the technique of substitution here. You must be clever enough to think in advance what could be your u, because when you let your secant x as your u, the derivative of secant x will involve secant x tangent x. So it's impossible to see it there exactly because there is an extra of tangent x, because this is the square of tangent x. So what if we will do the reverse? So when we rewrite this integrand like the tangent of x quantity squared, so I will write tangent squared x first here and then multiplied by secant squared x, and of course there is a partner of dx for the integral symbol. Now you must be clever enough that when you let your u be equal to tangent x, you realize that the derivative of tangent x is secant squared x, which can be found in our integrand here. So by substitution, that is equal to the integral of, instead of writing tangent x, you will write its equivalent expression, which is u. So u squared. And instead of writing secant squared dx, we will write its equivalent expression, which is du. So we write here du. And looking at this expression, we can readily think that we can apply our formula number 4 in the previous video, which is the power rule, that the integral of u squared is just u cubed over 3 plus c here. And going back to our original function, the value of u is tangent x. So this is 1/3 times the tangent cube x plus c. So this is our answer for our example number 1. Now let's proceed to example number 2 here. What is the integral of cosine x minus sine x all over sine x then dx? Now looking at this integrand, this is a little bit complicated because I cannot readily apply the formulas that we have here, because on the first place this is a rational function. Now one thing we can do here is to separate this binomial in the numerator. So I can rewrite the integrand like the integral of cosine x divided by sine x minus sine x over sine x. So I divide the two terms individually by sine x here. Now that I see that this is the integral of a difference, then we can apply our formula number 3, that the integral of a difference is just a difference of their individual integrals. So I can rewrite this like the integral of cosine x over sine x dx minus the integral of sine x over sine x dx. And then our integrand here in our first integral is still a rational function, but I can think in advance that when I let u be equal to sine x, which is our denominator here, I realize that our du here is cosine x dx, which can be found in our numerator here. So by substitution, we can rewrite this integrand as du. So instead of writing cosine x dx here, I will write its equivalent expression, which is du. So du over our u, because we let sine x as our u. But here in the second integral, that is the integral of 1 dx, because sine x over sine x is just 1. Now, looking at this expression, we can readily apply our formula number 5 in the previous video, that the integral of du over u is just equal to the natural log of u plus c. But we will group all the c's as 1 in the later part. And the integral of dx is the application of our first formula in the first lesson, that the integral of dx, the integral and the differential symbol cancels each other, and that is x. And we add up all the constant of integration as c. So going back to the original function, which is in terms of x, this is equal to the natural log of our u, which is sine x here, and minus x plus the constant of integration, which is our final answer in our second example. Now looking at these first two examples, we did not apply any of the formulas here, because in the first example we just apply our power rule, and in the second example we just apply formula number 5 and formula number 1 here. So looking at the integrand will not guarantee you that we can readily apply these formulas, because our integrand are in terms of trigonometric functions. So it's a matter of practice, it's a matter of experience here. So our third example is, what is the integral of the square root of 1 minus sine x dx? Now looking at this integrand, it is very difficult for you to apply right away formula number 8, because there is an exponent of 1/2 because of this radical symbol of square root. So if we rewrite this as the integral of 1 minus sine x to the power 1/2, that would not help in integrating that integrand. So this integrand may appear a little bit difficult. So what will you do is to apply a little algebraic manipulation here, that maybe we can apply rationalization in this part, that the integral of 1 minus sine x can be multiplied by an expression which is the square root of 1 plus sine x over the square root of 1 plus sine x here, and then dx. You should realize that this one is just equal to 1. So we did not alter the value of our original integrand. We just want to transform this one such that this integrand will be a little bit easier to integrate. So multiplying the two, this is equal to the square root of 1 minus sine x times the square root of 1 plus sine x over the square root of 1 plus sine x. I just join into one fraction. And you see that we can join the two square roots into one square root here. So this is the square root of 1 minus sine x times 1 plus sine x here. And this is divided by the square root of 1 plus sine x. And of course, we have still dx here. And when you multiply the two, that is equal to the integral of the square root of 1 minus sine squared x. Why? Because that is a product of sum and difference of two terms. Sum, 1 plus sine x, and difference, 1 minus sine x. So product of sum and difference is 1 minus sine squared x in our intermediate algebra. And of course, this is divided by the square root of 1 plus sine x. And we still have a dx here. And you can recall from your trigonometry that 1 minus sine squared x is the same as cosine squared x by Pythagorean relation in our trigonometry class. And the denominator can be expressed as 1 plus sine x to the power of 1/2 when you want to express this radical term into an exponential form. And we still have dx here. So this is equal to the integral of cosine x over 1 plus sine x to the power of 1/2, and then dx. Why? Because the square root of the square of cosine x is cosine x. And then you see that this is still a quotient of two functions. But that is not a problem, because if you can think in advance that if you let your u be equal to the expression that is being raised to the exponent of 1/2, which is 1 plus sine x, then you can realize that the derivative of this, which is equal to cosine x and then dx here, can be found in our integrand. So by substitution, we can have as cosine x dx, which is our du here. So instead of writing cosine x dx, we'll write du over our u to the power 1/2. And you think we can apply formula number 5, but actually it's not, because there is an exponent of our u which is 1/2. But that is very easy, because I can rewrite this like u to the power -1/2 du, when I want to place this term in the numerator, and you see that the exponent becomes negative. So with that, I can apply the power rule in our formula number 4, that is u to the power 1/2 over 1/2, because when negative 1/2 is added by 1, the result is 1/2, and there is a constant of integration c. So by simple algebra, we can multiply the numerator, which is u to the power 1/2, by the reciprocal of the denominator, which is 2 over 1. Now, we can go back to our original function, that our u is just equal to 1 plus sine x, but this is raised to the exponent of 1/2, and there is a constant of integration c. So this is our answer for our example number 3 here. Or you can rewrite this as 2 times the square root of 1 plus sine x plus c. Now let's proceed to our fourth example. What is the integral of dx over 1 plus sine x? Now you see, that's a little bit difficult. Why? Because if I let my denominator as my u, I cannot find my du in the integrand, because the derivative of sine x is cosine x, and I don't have cosine x there. So what will you do is to apply a little algebraic manipulation, that you must be clever enough. If you are an experienced person in calculus, I need to multiply this one by the conjugate of the denominator, which is 1 minus sine x here, so that you will not alter the original integrand. You must make your multiplier as 1. So multiplying our numerators, we have the integral of 1 minus sine x over the denominator of 1 minus sine squared x. Why? Because this is a product of two binomial, which is a sum and difference. And the product of 1 plus sine x times 1 minus sine x is 1 minus sine squared x in our algebra. And we still have here dx. Now I can apply a little identity here, that this is the integral of 1 minus sine x over cosine squared x dx, because I know that 1 minus sine squared x, it is identical to cosine squared x in our trigonometric identities. Now at this time, if I let my u to be cosine x, I cannot get the derivative as 1 minus sine x. So that's still a problem. So what I can do here is to separate, divide the binomial in the numerator by the denominator. So that is 1 over cosine squared x minus sine x over cosine squared x. And we still have our dx here. So we just divide the binomial by this denominator, so that we can separate the two terms in the numerator as two rationals. And we know that the integral of a difference is the difference of their individual integrals. So this is the integral of 1 over cosine squared x dx minus the integral of sine x over cosine squared x dx. And I can apply another identity here, that this is equal to the integral of secant squared x, because we know that 1 over cosine is secant, and we still have dx here. And so what I can do here in my second integrand, I can factor it out such that this is equal to sine x over cosine x times 1 over cosine x dx. And you can check that cosine x times cosine x is cosine squared x, and sine x times 1 is our numerator. Now I can apply our formula that our integral of secant squared is tangent u. So here, this is tangent of x. And I can apply a little identity here because sine x over cosine x is tangent x. And 1 over cosine x is secant x dx. And again, looking at this integrand, we can apply formula number 12 here. So this is equal to tangent x minus the integral of this, which is secant x, and then plus c, our constant of integration. And this is our answer for our example number 4. And you see, out of our 4 examples, it's only this example that applies some formula here. Because in our third example, it's just an application of the power rule in integration. So it's not a guarantee that when your integrand is in terms of trigonometric functions that you can apply right away these formulas. So at this point, I will proceed to my 5th example here. So example number 5. I will give here an example that would apply the first 2 formulas here. So what is the integral of sine 7x times cosine of 3x dx? This integrand is a little bit difficult for 2 things. Because first, it's a product of 2 trigonometric functions, sine 7x and cosine 3x. And we know that there is no straightforward formula for product in integration. Second, we don't have the same angle here because this is 7x and the other one is 3x. They are not the same. So, one thing we can do here is to recall our identities that we learn from our trigonometry. An identity that would convert the product of 2 functions into a sum or difference of these 2 functions. Like we know that sine alpha times cosine beta, this is equal to 1/2 times the sine of alpha minus beta plus the sine of the sum of alpha plus beta here. Also, we know that the sine of alpha times the sine of beta, this is equal to 1/2 times the cosine of alpha minus beta minus the cosine of alpha plus beta. Also, the cosine of alpha times the cosine of beta, we learn from our trigonometry that this is equal to 1/2 times the cosine of alpha minus beta plus the cosine of alpha plus beta. These are trigonometric identities we've learned from our trigonometry class in high school. So applying one of this one to our integrand, we can apply the first one here because this is a product of 2 trigonometric functions of sine and cosine. So we will let here our alpha as 7x and our beta as 3x. So applying this identity, this is equal to the integral of 1/2 times the sine of your alpha minus beta, and our alpha is 7x minus the beta of 3x. And then this is added to sine of alpha plus beta, which is 7x plus 3x here, and we still have dx. So I noticed that I have a factor here, which is a constant, that I can factor it out as 1/2 times the integral of the sum, which is sine of 4x plus the sine of 10x, and we still have here dx. Why 4x? Because we subtract here. 7x minus 3x is 4x, and 7x plus 3x, that's 10x. So moving down here, this is equal to 1/2 times the integral of sine 4x dx plus the integral of sine 10x dx here, because the integral of a sum is the same as the sum of their individual integrals. But don't forget that this sum is all in all multiplied by 1/2. So I can distribute the 1/2, say this is 1/2 times the integral of sine 4x dx plus 1/2 of the integral of sine 10x dx. And I can apply the U substitution here. So if we let U be 4x, this one, our du will involve just 4 dx. But I don't have 4 dx there, I have only dx, so I need to divide both sides of the equation by 4. So this is our value of dx. Also, I can let v, so I'm using here another variable for our 10x. And when we find dv, this is equal to 10 dx. But I have only dx here, so I can divide both sides by 10 so that I can find my dx here. So substituting these values to the original integrand, we have 1/2 times the integral of sine u. So instead of writing 4x, we will write the value of 4x, which is our u. And instead of writing dx, we will write the value, which is du over 4 here. And also this is added to 1/2 times the integral of our sine v. So instead of writing 10x, I will write v, which is the value of 10x. And instead of writing dx here, I will write dv over 10. So this is dv over 10. And you see that there are constants in the denominators of our du and dv. So I can factor it out that that is 1/8. Because 1/2 times 1/4, that's 1/8 times the integral of sine u du here. And this is plus 1 over 20 times the integral of sine v dv. So at this time, I can apply the formula number 8 here, that the integral of sine u du is equal to negative cosine u plus c. So this is equal to 1/8 times negative of cosine u. And our c will be grouped as 1 at the last. So this is added to 1 over 20 of negative cosine v, because this one is in terms of v, and added all in all to our constant of integration c. So going back to our original variables, we have negative 1/8 times the cosine of 4x, because our u is 4x, minus 1 over 20 of cosine 10x plus c. And this is our beautiful answer for our example number 5. So our lesson here is that we cannot readily apply right away these formulas even if our integrand are in terms of trigonometric functions. We need to apply some algebra, some manipulation so that it can be formatted the same as our formula here. And second, we will apply a lot of trigonometric identities so that you can transform the integrand into a form which is the same in our formula here. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.